Hi there. In this video, we are going to take the definitions that we've established for sine, cosine, and tangent and extend them so that they can apply to angles that are larger than 90 degrees. Because right now your definition of sine, cosine, and tangent is a little bit limited. You might not even realize it to only certain angles. But we've seen that angles can have any measurement they want by rotating them around multiple times or even in the negative direction. So we'll show you how those angles can have sine, cosine, and tangent as well, not just acute angles. So here we go. Okay, this information is found in your book. So if you're looking for something to follow along with, it starts on page 433 and goes on to page 444, and it's really just those two pages that we're looking at. So we will be defining the trigonometric ratios for all angles, not just acute angles, and we do so by using the coordinate plane, the xy axis. Currently, your definition for sine, cosine, and tangent works really well as long as your angle is acute. Sine is established as a ratio of the opposite leg divided by the hypotenuse. And if my angle is acute, I can place it inside of a right triangle, find those lengths of the sides, and create my ratio. But angles don't have to be acute, which means that they wouldn't fit inside of a right triangle. So trying to identify which leg is the opposite leg and which side is the hypotenuse here is something that I just can't do. However, angles larger than 90 degrees do have trigonometric ratios associated with them. You could use your calculator and find the sine of a 135-degree angle, and it would give you a value. We just need to understand now where that value comes from and how we could find it on our own. To do so, we're going to take our sine, or rather our angle, and place it in the coordinate plane. So to define trigonometric ratios for all angles, we place our angles in the coordinate plane and relate the sides of the triangle to coordinates that our angle passes through. And I'll show you what I mean right here. So there's that same triangle with sides of 3, 4, and 5, but now I've placed our angle theta and the parts of this triangle in the coordinate plane. If this side is my initial side, and this side is my terminal side, because remember we think of angles as rotating around the origin before they reach their final resting place, I can think now not in terms of how long are these sides, but I can relate those lengths to a point that the angle's terminal side passes through. The x-coordinate 3 corresponds to this leg, and the y-coordinate 4 corresponds to this leg. And we'll talk about what the hypotenuse would correspond to. The sides that we formerly thought of as adjacent and hypotenuse can now be described in terms of this point. The side we thought of as adjacent relates to the x-coordinate that the terminal side passes through. The side we thought of as opposite relates to the y-coordinate that the terminal side passes through. And that length of hypotenuse represents the distance from this point to the origin. Now I could find that distance by essentially doing the Pythagorean theorem. I could take 3 squared plus 4 squared, and that would be equal to that distance squared. So taking the square root of this would find that length for me. And I can prove that to you here. This is the root of 9 plus 16, which is the root of 25. So that distance from the point to the origin is 5. Putting those parts together, we can create some new definitions of sine, cosine, and tangent that rely on the coordinates of a point that your angle passes through. And these coordinate definitions are found in your book on page 444. We'll go through them here as well. So let theta be an angle in standard position, and let P with coordinates xy be a point on the terminal side of theta. R would be the distance from this point to the origin, and we could calculate that R again by thinking in terms of the Pythagorean theorem. X squared plus y squared would be r squared, so I take the square root of both sides. With those pieces in mind, we can create some definitions of sine and cosine and tangent that rely on this coordinate rather than the sides of a triangle. For example, the sine of that angle, instead of thinking in terms of opposite divided by hypotenuse, now the sine of that angle can be described as the y coordinate that the angle passes through divided by that length r. Likewise, the cosine of that angle, rather than thinking in terms of what's the opposite leg divided by the hypotenuse length, the x coordinate that the angle passes through stands in for that adjacent leg. I misspoke earlier, I should have said adjacent leg, and the distance r would be your hypotenuse. And of course, tangent follows suit as well. To find the tangent of an angle, you can still use a triangle, but if you know the coordinates that that angle's terminal side passes through, you could find that angle's tangent by taking the y coordinate that it passes through and dividing it by the x coordinate. These definitions of sine, cosine, and tangent are very useful because they would allow you to find the sine or cosine or tangent of an angle that's not an acute angle and wouldn't fit inside of a right triangle. You could find the sine or cosine or tangent of that angle as long as you could identify the coordinates of a point that this angle passes through. And we'll do an example of that in a moment. Now, each of these ratios does have that same reciprocal ratio. The reciprocal of the sine is the cosecant, the reciprocal of the cosine is the secant, and the reciprocal of the tangent is the cotangent, and all those same definitions follow. To find the cosecant of an angle, why, that's the reciprocal of the sine, r over y. To find the secant of an angle, that's the reciprocal of the cosine, r over x. And to find the cotangent of an angle, that's of course the reciprocal of the tangent, x over y. Memorizing these definitions is a great idea because it'll help you again to find the sine, cosine, or tangent of an angle when you are able to locate a point that it passes through. Sorry, my pens are clattering all over the place. Let's show you an example of this, and there is right below on page 444 an example similar to the one that I'm about to do. We are asked to find the sine, cosine, and tangent of an angle whose terminal side passes through the point 3, -2. SOHCAHTOA doesn't help us here because the measure of this angle would not fit inside of a right triangle. In fact, I don't even know whether the measure of this angle is positive or negative because we've seen that angles can rotate in different directions. Maybe this represents the measure of that angle theta. Maybe it's a positive angle that's rotated almost all the way around the circle. Or maybe this is that angle theta rotating clockwise, again, is a negative measurement. And in fact, the measure itself doesn't really matter because we are provided with the coordinates of a point that the terminal side of my angle passes through. I know it passes through the point 3, -2. So I can use these coordinate definitions to find the sine, cosine, or tangent of this angle by utilizing this point. The sine of this angle theta is y over r. So I know the y coordinate is -2, and I'll find that distance r by using what is again essentially the Pythagorean theorem. Let's do that work right here. R is equal to the root of x squared plus y squared. That would be 3 squared plus -2 squared. That would take me to 9 plus 4. Remember, a negative squared is positive. And I would find that the distance from that point to the origin is the square root of 13. So the sine of theta would be equal to the y coordinate, -2. And my color coding is getting all goofy, so let's just go black ink. -2 divided by this distance, root 13. Always rationalize your denominators. Don't leave a square root in the denominator. So the sine of theta works out to be -2 root 13 over 13. Notice something unique is happening here that we wouldn't see if we were using SOHCAHTOA on a right triangle. The sine of this angle is a negative ratio. And that's because this angle's terminal side passes through a point whose y-coordinate is negative. Will we get a negative value when we find the cosine of theta? Well, the cosine of theta on the coordinate plane is defined as x over r. And the x-coordinate that this angle passes through is +3. The distance to the origin from that point is the square root of 13. Rationalizing my denominator, I find that the cosine of this angle is +3 root 13 over 13. So I did not get a negative value for my cosine because this angle's terminal side passes through a positive x-coordinate. Lastly, for this example, will we get a negative tangent ratio? Well, the tangent was defined on the coordinate plane as y divided by x. The y-coordinate that the angle passes through is -2. The x-coordinate is +3. Therefore, the tangent of this angle theta is -2/3. So unique here that our ratios of our angles, our trigonometric ratios, can now sometimes be negative values depending upon the coordinates that this angle passes through. Now, since this angle passes through a point in quadrant 4, it's not too surprising that the sine is a negative value, because whatever the coordinate might be, if it lies in quadrant 4, the x value is positive and the y value is negative. And that's why we got a cosine that's positive. We're going to do one more example here, and that's with one where they didn't provide us with the coordinates straight out, but gave us some information that we could utilize to find those coordinates. The terminal side of an angle of theta radians lies in quadrant 3. So it's here in quadrant 3, that terminal side, and it lies along a line whose equation is y equals 2x. Find the sine, cosine, and tangent of theta. To do so, I first need to find the coordinates of a point that the terminal side passes through. That's what my definitions rely upon. I don't have a triangle to use for this one, so I have to use an alternate definition that relies on the coordinates of a point that the terminal side passes through. The initial side of the angle always lies along the positive x-axis, and my terminal side is somewhere here in quadrant 3. How can I find the location of that terminal side? I utilize this equation that they gave me. Y equals 2x is the equation of a line with a slope of 2 and a y-intercept of 0. Think back to your Algebra 1. If the slope is 2, I could use a rise over run of up 2 and over 1, but that would be heading into the first quadrant when I want to go into the third quadrant. So I'll use that same slope and go down 2 and over 1 to locate a point that's on this line. I could even go down 2 again and over 1 to find the coordinates of another point. Those coordinates help me to represent where the terminal side of this angle lies. It's right there. And it's also provided me with not just one, but two x, y coordinates that the terminal side of this angle passes through. And I could use either one of these two coordinates to now find the sine, cosine, and tangent of this angle theta. Theta rotates in the positive direction, looks like that. Or heck, even if theta rotates in the negative direction and looks like that, isn't important now because I know the coordinates of an angle that this, rather the coordinates of a point that this angle passes through. Got a little mixed up there. So the sine of theta using our coordinate definitions is y over r. Let's find r, and I'm going to use this point because the numbers are smaller. Smaller numbers always make our lives a little bit easier. We'd have -1 squared plus -2 squared underneath our square root. That'd be the root of 1 plus 4, so that value for r is the root of 5. Therefore, the sine of this angle theta is equal to -2 over root 5, which rationalizes to -2 root 5 over 5. Again, I got a sign that was negative because this angle passes through a y-coordinate that's negative. The cosine of theta, and again, study those coordinate definitions, get those locked in your brain just as tight as you've got SOHCAHTOA, is -1 over root 5, which would rationalize our cosine ratio to -root 5 over 5. This time, our cosine ratio is also negative because this angle passes through a coordinate where the x value is negative. Will we have a tangent ratio that is positive or negative? Well, the coordinate definition for tangent is y over x. In this case, that would be -2 over -1. Therefore, the tangent reduces to +2. And we get a tangent that's positive because both x and y are negative, and the quotient of two negatives is a positive. Also, the tangent is a great way to show you that if I had used these coordinates instead, I'd still get the same ratio because my y, -4, divided by my x, -2, reduces to the exact same tangent. I also confirm the fact that I know that anytime a coordinate lies in quadrant 3, its x value and its y value are both negative, which makes me feel pretty good that I got a negative value for my sine ratio and a negative value for my cosine ratio because both those x and y coordinates are negative. And the tangent should be positive once again because that quotient. Large takeaways from this lesson that I hope that you can find that sheet here, would be these definitions of sine, cosine, and tangent that no longer rely on the sides of a right triangle, but are defined based on a point that your angle passes through. Hopefully you found this informative. Let me know if you have any questions, and have a great day.